Well, we have done predictions for decomposition reactions and predictions for synthesis reactions. The next set of reactions that we want to deal with are single displacement reactions, and in order to predict these, you're going to need to use an activity series of metals to determine whether a reaction will occur or not. One of the things that we want to be very careful about in chemistry is that when we write a chemical equation, that it represents something that is true. And so the activity series will help us to predict whether the reaction we want to write will happen or not. And your textbooks will all have an activity series in it. If you look in your index, it'll take you to the page. Students here at Ontario High School are given a copy of an activity series to use, so your teacher may have already provided that for you. So if no reaction occurs, we write NR, or just put a circle with a slash through it to show that no reaction occurs. And you can see here I've written a reaction for solid copper added to aqueous aluminum chloride. And when you look at your activity series, copper is below aluminum on the activity series, meaning it's not as active, and it will not displace aluminum from the solution here. So we write the no reaction. Now for the next reaction, I have aluminum metal being added to copper 2 chloride, and in this case aluminum is above copper on the activity series, so this reaction will occur. And what will happen is the copper will come out of the solution as a solid, and the aluminum will dissolve into the solution, and so you have an aqueous solution of aluminum chloride and solid copper metal as a result. So aluminum higher on the activity series, some more active metal, so it can displace copper from the aqueous solution. Copper metal cannot displace aluminum from an aqueous solution. Here is a list of some possible single displacement reactions, and you'll see if the reaction occurs, the products are written. If the reaction does not happen, then NR is written showing no reaction. Now again, when you check this, as we look at our first reaction, we have solid copper being added to aqueous silver nitrate. The metal that's by itself on the reactant side has to be higher on the activity series than the metal that's in solution in order for a reaction to occur. So copper is higher, so it will replace silver in the silver nitrate. And one of the things that you want to look at as well is you have to write a formula if the reaction occurs for the ionic compound that's in aqueous solution on the other side. And copper is a metal that has more than one oxidation state. When I'm dealing with transition metals other than zinc, silver, and cadmium, which have just a single oxidation state, if I'm not sure what to use, I will often default to a 2+, because almost all transition metals that have multiple oxidation states will have a 2+ state. And so in this case, I go to copper 2 nitrate, aqueous, and the silver solid. My next reaction, I have silver solid being added to copper 2 nitrate solution, and you'll see here that there's no reaction. Silver is lower than copper on the activity series, so it will not displace copper from the solution. My next reaction, I have sodium metal being added to iron 3 chloride, and sodium is higher than iron on the activity series, so the sodium will displace the iron and form aqueous sodium chloride and iron metal. And then again you see here the next reaction, we have iron being added to aqueous sodium chloride. Because iron is lower than sodium, there's no reaction. Next we have magnesium being added to liquid water, and there is no reaction here. And if you'll look on your activity series, most of them will have some commentary regarding the activity of metals. And when you look at magnesium, it will not displace hydrogen from cold water. But in the next reaction, you can see that magnesium will displace hydrogen from steam to form magnesium oxide and hydrogen gas. So you need to make yourself aware of those other things that the activity series can tell you. And so while magnesium will not displace hydrogen from cold water, liquid water, it will displace hydrogen from steam. Now, the last two reactions, we have halogens involved. And it's very important that when you look at single displacement reactions, metals can replace metals. Non-metals can replace non-metals, and in this case we're going to deal with halogens, but a metal will not replace a non-metal, and a non-metal will not replace a metal. So it's very important that you know what you're going to replace here. So here we have chlorine gas being added to aqueous sodium bromide, and the some activity series of metals will also include a section that shows the activity series of halogens, but you really don't need that because you can look at your periodic table. And as you look at your periodic table, the halogens are arranged in their group from top to bottom, fluorine, chlorine, bromine, and iodine. And that's really its own activity series. Fluorine can replace chlorine, bromine, and iodine. Fluorine's much more active than those other three elements. Chlorine can replace bromine and iodine, but it cannot displace fluorine. Bromine can displace iodine, but it cannot displace fluorine and chlorine, and iodine won't displace any of the three elements above it. So you really don't need the a separate activity series from that because the periodic table just delineates that really well for you. So again, here you see the chlorine displacing the bromide to form sodium chloride and bromine, and please note that there will not be a combination of chlorine and bromine. The chlorine replaces the bromide ion. The bottom reaction, we have bromide being added to aqueous sodium chloride, and here there would be no reaction because bromine is not as active of a halogen as is chlorine. Well, time for you to try some single displacement reaction predictions. So here are a list of the products of possible single displacement reactions. Use your activity series to predict, first of all, whether the reaction will occur. If it does, then write the products and balance the equations. And you can pause the podcast, and once you've got the equations done, then resume the podcast and check your answers. Welcome back. Let's see how you did. The first reaction, we have barium metal being added to liquid water. Barium is above hydrogen on the activity series, so this reaction will occur, and the products will be barium oxide and hydrogen gas. In the next one, we have calcium metal being added to iron 3 chloride, and calcium is higher than iron on the activity series, so it will form calcium chloride, aqueous, and iron metal. On the next one, we have nickel being added to aqueous magnesium bromide. Nickel is not higher than magnesium. It is lower than magnesium on the activity series, so no reaction will occur. Our next reaction, we have fluorine gas being added to potassium iodide, aqueous potassium iodide. The fluorine is a more active halogen than is the iodine, so fluorine will displace the iodide ion here and will form aqueous potassium fluoride and iodine, elemental iodine. In the next one, we have copper metal being added to aqueous zinc chloride, and here, because copper is lower on the activity series than zinc, no reaction will occur. Zinc is a more active metal, so it will not be displaced by copper. On the next one, we have chlorine gas being added to sodium fluoride, and because chlorine is lower on the periodic table than is fluorine, we can predict that this reaction will not occur. And finally, we have magnesium metal being added to hydrochloric acid, and in this one you'll form magnesium chloride, aqueous magnesium chloride, and hydrogen gas. So, how'd you do? Well, we're through predicting decomposition reactions, synthesis reactions, and single displacement reactions. So now we want to look at double displacement reactions. And we're actually going to look at three types here. The first type are double displacement reactions in which precipitate forms. So in these, the cation of one reactant forms a solid in aqueous solution with the anion from the other reactant. And these can be predicted using solubility rules. And you'll notice the note here, the solubility rules must be memorized. So your textbook will have a set of solubility rules. For students at Ontario, I give you a set of rules that I think are a little bit easier to memorize than that which is in the textbook. You can always go online and find multiple copies of different instructors' solubility rules. Find one that makes sense to you and memorize those. It's the only way to predict these correctly. This first set of double displacement reactions that are precipitate forming reactions, the first reaction here we have is lead-2 nitrate aqueous being added to aqueous potassium chloride. The lead-2 ion and the chloride ion are not compatible together in aqueous solution. So that will come out as a solid precipitate. So we see the lead-2 chloride written as a solid. And then aqueous potassium nitrate. The potassium and the nitrate ions will stay dissolved in the aqueous solution together. In our second reaction, we're adding aqueous ammonium nitrate to aqueous sodium sulfate. And here there would be no reaction. And the reason for that is the ammonium ion and group 1 metals such as sodium, these are compatible pretty much with everything that's common that you'll run into. So because no precipitate forms, on the other side of this reaction, if we write these products, we would have ammonium sulfate, which would be aqueous, and sodium nitrate, which would be aqueous. When there's no change in phase on the product side from the reactant side, it means no reaction has occurred. And later on, we'll have a podcast that deals with writing net ionic equations, and we'll talk about what happens when we dissolve ionic compounds in solution. And again, as long as there's no change in phase, no reaction has occurred. In our final reaction here, we're reacting aqueous calcium chloride with aqueous sodium sulfate. When we do this, the calcium and the sulfate ions are incompatible in the solution, meaning that they will form a solid precipitate. And so we have the CaSO4 solid, and then the sodium chloride, those ions will remain in aqueous solution. Another type of double displacement reaction that we'll look at is a gas-forming reaction. And this is a very common one in which an acid added to a carbonate will form a salt, which is an ionic compound, water, and carbon dioxide gas. So our example here is we have hydrochloric acid being added to sodium carbonate, and this can either be a solid or aqueous, and it will form aqueous sodium chloride, liquid water, and carbon dioxide gas. So when you see an acid added to a carbonate, predict the metal salt that will form, liquid water, and carbon dioxide. A third type of double displacement reaction are water-forming reactions that we'll also call neutralization reactions. In these reactions, we'll have acids being added to metal hydroxides, which are basic, and they form a salt in water. So our example here is aqueous hydrochloric acid being added to aqueous sodium hydroxide. We form sodium chloride, aqueous, and liquid water. So the water is neutral. Sodium chloride does not affect the neutrality of this solution, so this is a neutralization reaction. So when you see an acid added to a metal hydroxide base, form a salt and liquid water, and that's the special type of double displacement reaction that this is. So let's predict the products and phases of the following reactions and then balance these equations. And again, go ahead and write these down on a piece of paper. pause the podcast, make your predictions, and then resume the podcast when you're ready to compare your answers to mine. Welcome back. Let's see how you did. In this first reaction, we're mixing aqueous solutions of sodium chloride and magnesium sulfate. When you check to see if a precipitate will form, you take the metal from one compound, combine it with the anion of the other compound. So we'll look at sodium and sulfate together. Those would be soluble because group 1 metals are essentially soluble with everything. Then we'll look at magnesium and chloride ion, and we know from our solubility rules that metal chlorides are soluble with everything except for silver, lead 2, and mercury 1. So the magnesium and the chloride would be soluble as well, so no reaction would occur here. In the second reaction, we have aqueous solutions of calcium chloride being added to an aqueous solution of potassium carbonate. We know that potassium chloride would be soluble because group 1 metals are soluble with everything. We know also that chlorides are soluble with everything except for silver, lead 2, and mercury 1. So in this case, we would be looking at calcium and carbonate and seeing if that would be a precipitate that would form. And in our solubility rules, we'll find that carbonate ions are only soluble with group 1 metals and ammonium. So calcium carbonate would form a precipitate. This would be insoluble in water. So calcium carbonate solid would form along with aqueous potassium chloride. In the next reaction, we have an acid, sulfuric acid, being added to a metal carbonate, and this is one again where you want to form carbon dioxide, liquid water, and a salt. In this case, the salt would be calcium sulfate, CaSO4. So this reaction would occur, and these are the products of that reaction. And finally, the last reaction, we're adding phosphoric acid, H3PO4 aqueous, to a metal hydroxide, sodium hydroxide, and forming sodium phosphate and liquid water. So how'd you do? If these areas seem like a mystery to you still, don't hesitate to rewind the podcast, watch it again, read through your textbook, make sure that you have the solubility rules memorized, that you know how to write these formulas for the salts that will form. All that can be very helpful to you, and there are some past podcasts that go through these things very thoroughly, so don't hesitate to look at those. This is the end of the Ontario High School Chemistry video podcast regarding predicting reactions. I wish you well with this.